another question now. This will be our last question based on this particular small concept. And the question is saying that there is a charge. This charge is falling down under the influence of gravity. Okay, it is falling down under the influence of gravity, and it falls in a region. It is falling. It suddenly comes across a region where the magnetic field is pointing towards the north. Now, students, what I would like to tell you is basically almost every question in your magnetism, in the subject of magnetism, is mostly taken inside. It is the magnetic field is always, not always. See, it is usually taken inside, and so we will do that. So you can imagine this is falling under gravity. This charged particle falls under gravity. There's a magnetic field which is pointing towards the board, which is going inside this board right now. Then can you tell me where will be the deflection? Suppose this q is greater than 0. Of course, we are talking about a positive charge.
Sir, towards east.
Let's say one minute. Let's say that it is a negatively charged particle. The question was a negatively charged particle. Yes. Someone said towards east. Okay, no problem. See, for a negatively charged particle, okay, can you all tell me? All of you all are participating, right? How many students are there right now who are listening to me? So please, each one of you all can answer the question. Each one of you all can answer the question right here, right now. If the velocity, if gravity, forget this, it is under the influence of gravity, but it is having some velocity v. And if you use your right hand thumb rule, basically, with the magnetic field inside and the velocity in this direction, okay, let me show you. Magnetic field like this towards the board inside, and velocity vector like this. Shift it down like this and apply the right hand thumb rule. If you apply the right hand thumb rule, okay, you're getting a force which is on the right side. You're getting a force which is on the right side. So if you're getting the force on the right side here, I will just put the point here, and I'm getting v cross v to be here. But students, this is a negatively charged particle. And if it is a negatively charged particle, so in that case, the force will be opposite to v cross v. Yes or no? So now in the question, it was written that the magnetic field is basically in the direction of north. So if the magnetic field is in the direction of north, by basic geometry, if I make it in 2-dimensional, let's consider this to be north. This is south. This will be east, and this will be west. So in this case, north is basically the direction of the magnetic field which I have taken inwards. Okay. So what are you getting here? Can you see the force is in which direction? The force is in west direction.
West.
It's in the west direction. So this was a small concept based on direction itself, and I hope you have understood this. If there is any doubt, let me know. Simple thing, that a charge is falling under the influence of gravity. You apply the right hand thumb rule, that is always velocity into the magnetic field, v cross b. Never do it opposite. Okay, that's wrong. So always take your fingers, point it in the direction of the velocity vector which is going downwards, curl your fingers here, and you will get, curl your fingers to the b vector, the magnetic field vector. You'll get v cross b to be in this direction. But since our specified object here, charge, is basically a negative charge, the force will be in the opposite direction, and this should be very clear. So let's come to one important topic, and this important topic is basically the motion of a particle in the magnetic field. Okay, motion of a charged particle. I will write it here. It's an important topic. And so this is an important topic. How can we define the path of a charge? Basically, that's the topic. So suppose, let's say that there is a magnetic field which is pointing inside this board. Let's take it normally as we take it. Okay, No confusion here. The magnetic field is basically inside the board. Great, no problem. And I am saying that this magnetic field is basically all over the board. You can imagine it is all over the board. And now I place a charge here. I place, let's say, a charge at this point here, and I give it some certain velocity. I give it some certain velocity. Then, can you tell me where is the force going to be? All of y'all, please participate. Please participate. Where will be the force? In which direction? Will it be up, down, left, or right? Which direction?
Sir,
Which
up.
direction?
Up.
It will be up. See,
Upwards.
take your right hand towards the velocity vector and curl it across the magnetic field. You will get the direction upward. So here, students, the force is up. The force is up. So can I say that somewhere along this line, or somewhere in this path, the path of my charge is going to be like this. But at this point right here, okay, where is the velocity vector pointing? It is pointing top. So, and if velocity vector here is pointing on the top, is pointing upwards, then the force is in which direction? Force is in which direction? Apply right hand rule towards the velocity vector. Curl your fingers to the magnetic field. Where are you getting? Where are you getting a magnetic force? You're getting towards the left side.
Left.
Getting it towards the left, student. See, listen. And then suddenly, if it is towards the left, that means the path is going to be like this. Now let's find out what is going to be the force in this direction. So here you can see that again, the velocity vector is now in this direction. And if you apply right hand thumb rule, it will be difficult for me to demonstrate right now. But you can imagine right now that where is the force going to be? Apply right hand thumb rule towards the velocity like this and curl it. Where are you going to get it? You're going to get it downwards, isn't it? You're going to get it downwards. So the force here will be downwards. And so what are you getting finally? At this point here, velocity vector is again going to be in which direction? It's going to be downwards. So if velocity vector is here, then the force is again inside. And students, can you see what is being formed here? Can you see what's being formed here?
Circle.
Okay, what a circle is being formed. So students, this is an interesting thing. This is an interesting thing. Basically, we are trying to understand the motion of a charged particle in a uniform magnetic field. In a uniform magnetic field. Why is that important? Okay, uniform magnetic field is important. Uniform. Please remember, we will not be doing all our cases in uniform magnetic field, but right now our magnetic field is uniform. They are equally spaced. And so when you move a charged particle with a certain velocity like a carom board, what is going to happen is it's going to have some velocity vector, say suppose in x direction. Then the force is always perpendicular to the velocity vector and to the magnetic field. You can see that this force is basically 90 degrees with the velocity vector, and it is 90 degrees with the magnetic field, which is going inwards. And similarly, since the force is pointing inside, we are getting a circle like this. Every time, at every point here, students, the force is pointing inside. The force is pointing inside. And do you know what this force is called? Students, can you tell me what is this force called? What is this force called?
Centrifugal force.
Centripetal force, students. Centripetal force. Correct, correct. So centripetal force. But now, okay, this centripetal force is observed. Where all it is observed? If you're sitting in a car, the car suddenly moves from right to left. Then you move from where? You move inside from left to right. That is caused by centripetal force. Yes, students. Yes, right, correct. So if force is inside, then we know by this formula that the force can be equal to centripetal force, and centripetal force is given by what? Is given by what? You remember this formula, mv square by r. Students, you remember this formula? This is centripetal force formula. Nothing so difficult. Okay, just even if you don't remember that centripetal force is denoted by mv square by r. Okay, and in this case mv square by r, but we also know in the previous lecture, students, that force is equal to what? Force due to this magnetic field is what? Can you tell me what was the formula? Okay,
QVB.
it is Q. V cross B, yes or no? And in this case, we can see that the V cross B is inside the plane. V is perpendicular to the velocity. So what are we going to get if we open this cross product? QVB sine 90. QVB sine 90. And sine 90 becomes 1. So basically we get QVB. So I have two equations now, students. I have two equations. One is F is equal to mv square by r. And my second equation, F is equal to QVB. So why with these two equations, students, with these two equations, can I say that, let me just shift the board. Let me just shift the board. And so can I say with the two equations that basically my mv square by r is equal to QVB? Can I say that? Yes or no, students? QVB.
Yes, sir.
And so students, with this formula right here, we are able to find out the radius of this path in a radius of the path of a charged particle in a uniform magnetic field, which can be simply R is equal to what, students? Can you tell me? R is equal to mv square by QVB, and here V and V will get cancelled. So R is equal to mv upon qb. So students, the radius of this path r is equal to mv upon qb. But students, what I'm saying right now is this formula is not important. This formula is not at all important. Listen to me. This is the most this is where I want to catch you all, and I want to explain you all that here it is about the concepts. Someone told me when the force they saw, when some student told me that they saw the force right inside, going inside, then someone told me that force is basically a centripetal force. Good, that is a concept. Now you know the formula because you've been using it 1,000 times. F is equal to mv square by r. Now what else we know? That the force because of a charged particle in a uniform magnetic field is some charge q, which we are considering, into v cross b. You find out the angle between v and b, you got sine 90. F is equal to qvb. And then what you said is basically you related kinematics with what? Magnetism. You related kinematics with magnetism. What did Oersted, the scientist, what did he relate? He related electrostatics. He related electricity with magnetism. Okay, these are not things to by heart. So here you can see that kinematics is being related with magnetism. And so with this right here, with this relation, these two relations right here, we are able to derive this radius. This radius of this path. So next, you can understand that in questions, in many questions in your NCERT books, what you'll see basically is you might see that not always this derivation is basically done in ideal form. It's done in ideal form. Questions are going to be in such a form, they're going to tweak the parameters of this. Somewhere you will see that the magnetic field region is going to be half. If it is half, then what will be the path? And in that case, what will be the radius? If it is full, this is the radius. In other words, in other questions, you might find that if the magnetic field is not uniform, then what will be the radius? What will be the path? So those are things you have to think on. That is physics. So anyways, we found out that the radius here is going to be equal to mv by qb. Great, we know this, mv by qb. But what is the next parameter? What can we else we can find out? We can find out time period. Why time period? Let's put more kinematics in this. What is going? Time period is also in your AC circuits. You remember that? Okay, that will come to. So time period here is basically the charge moving one rotation per unit time. So how much does it take? So what is the formula for time period, children? It is going to be what? 2 pi. What is it going to be? 2 pi by omega. You remember this? 2 pi by omega, where omega is the angular frequency. Yes or no? Angular frequency omega is given by what? V by R is given by V by R. Substitute that, students, substitute that V by R over here. What will you get? You'll get T is equal to what? T is going to be equal to
2 pi r by v.
2 pi R by V, students. But now, okay, you found out the time period in a general situation. But in this when we are relating this, we know what is r. We know what is r. So substitute the value of r over here in this format. Substitute the value of r in this format. What will be the time period be? What will be the time period? Students, tell me what is going to be the time period. Fast, quick, 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 quick. So what are you going to get? T is going to be equal to what? 2 pi by v. Keep the value of r, that is mv upon qb, and so you can see v and v get cut. So T is going to be equal to 2 pi m upon qb. 2 pi m upon qb. So this is the time period. This is the time period. But now we have found out time period, students. Time period. So what else can we find out now? If we have found out the radius, okay, we found out time period. Now we found out time period. Then what is 1 by t equal to? What is 1 by t, students? Can you tell me what is 1 by t? Frequency. Come on, let's find out how many times the rotation is done per unit time. Okay, that is frequency. F, denoted as f. F is equal to small f is better. Okay, general method will do. F, small f, okay, is equal to 1 by t, and that is equal to what? QB upon 2 pi m. So this is the frequency. F is equal to QB upon 2 pi m. So these are three general formulas which you should know, and this you will know by constantly practicing questions. Don't by heart. Okay, not every time you will know, you will remember this. If you don't remember, simply derive it in your head. That's it. Okay, so R, if you know time period. Time period, if you know frequency. These are three important terms of this chapter. Three important terms of this chapter. Okay, so if this is understood, students, then we can go to basically the work done. What is going to be, since we know all this now, okay, let's think of the same topic right now. Let's say that the magnetic field, students, is inside this board. Magnetic field is inside the board, and so if it is inside the board, and I just now told you, if I move a charged particle with a velocity v, what is the path we are getting? What is the path we are getting? So we get a circle. So if we are getting a circle, students, if we are getting, sorry for my imperfect drawing, but here you can see that the velocity vector and the force, is going to be perpendicular to each other. Yes or no? So let's talk about this topic called work done. Work done by whom? Work done by magnetic field. Magnetic field. Work done by magnetic field. On what? Work done by magnetic field? On a charge in a uniform situation, in a uniform magnetic field situation. So in that case, students, can you tell me what is work done's basic formula? What is the work done's basic formula? Work is equal to force into displacement. Force, yes, students. So apply. Work is equal to force into displacement. But right now, what is the displacement here? What can we take the displacement here? We can take work done to be equal to what? We can take it as the radius. Okay, displacement here is in terms of radius. So I can say that dw is going to be f into dr. Okay, I will remove that into sign, otherwise it looks like a cross product. So in this case, work done is equal to f dot dr. And so what is r, students? What is r? R is equal to mv upon qb. Yes or no? mv upon qb. This is what we found out. So what is the work done in this situation? Students, can you tell me? What is the work done in this situation? What is the work done in this situation?
F in
Your voice is not clear.
F into mv upon qb.
Yeah, so what will you get? Will there be any work done? What is the work done? What is the quantity you will get? What is the okay, that we know. That we know.
MV square.
Okay, see, students here, look here. See, look here. Force here, this force here, no, is perpendicular to what? Is perpendicular to velocity here. Force is perpendicular to velocity. So let's write that. Force is basically perpendicular to velocity, and velocity, students, can be written as what? Velocity can be written as rate of change of distance with respect to time. Yes or no? So basically, can you see, if force and dr by dt are basically what? Having perpendicular relation between them, then can I say theta is going to be equal to what? 90 degree. Can I say theta is going to be 90 degree? And so what will be the work done then in that, students? F dot F dr cos theta. F dr cos 90 degree. So
0.
what is cos 90? So remember, students, that the work done, students, remember the work done by the magnetic field. Okay, work done by the magnetic force on a charged particle, because we are talking about a magnetic force right now. Okay, magnetic force, we're talking about magnetic force. The work done by magnetic force here, okay, students, is 0 on a charged particle. Okay, on a charged particle, when the velocity, okay, when the velocity and the force are perpendicular to each other. Okay, force is perpendicular to velocity. At that point of time, you can say that F is perpendicular to V. Write V in terms of dr by
So is it
dt.
conservative?
What are you saying?
So is it conservative?
Is it conservative? We'll come to that topic. We'll come to that topic. Don't worry. So right now, okay, listen to me. So if the force done, okay, is if the theta is equal to 90 degree, if basically we understand that these are 90 degree, there's a relation 90 degree, then we can always say that the work done is equal to force into displacement, and it is going to be equal to 0. So always remember this, students, that the work done by a magnetic force on a charged particle is 0, as force is perpendicular to velocity. As force is perpendicular to velocity. Okay. Okay. So if this is understood, okay, let's do a small summary. Okay, because this is going to be important as we enter a summary on based on both our lectures. Simply, students, now you should help me. Summary should be quickly done. Okay, for example, if I'm taking a conductor to have current outside, and there is a field around this conductor, and the field is having a direction in such a way, then you can simply use your right hand rule. You can use your right hand rule around the magnetic field. Of course, this is what? B. Okay, and this is a conductor here with current outside. If you have to anyway find out the direction of the current, all you have to do is take your right hand, okay, curl it around the magnetic field, and you will get the thumb pointing towards you. That means the direction of the current. But in contrary, you can also play this in the opposite way. If you know the direction of the current and the magnetic field direction is not given to you, simply use your thumb, put it on the conductor in the direction of the current, of course, and if you curl your fingers, you will get the direction of the magnetic field. Okay, similarly, if it was in this way, if it was in this way, then what would have been the direction of the current, students? Can you tell me? Simply, okay, direction of the current, you put your thumb in the place of a conductor which is going inside, current is going inside, curl your fingers, and when you curl your fingers, you're basically getting clockwise direction. So you get your magnetic field in such a direction. So if this is understood, second thing what we had discussed is basically in a magnetic field, in a uniform magnetic field like this, okay, if there is a charged particle, let's say it is here, q is here, and this q is having some certain velocity like this, then in that case, students, b is inside here, right here. So in that case, apply your right hand rule, place your four fingers in the direction of the velocity vector here, because ultimately we are trying to find out force which is proportional to v cross b. And so, okay, both are vectors here, and so if you use your if you find out v cross b using right hand thumb rule, you will get the force. So v is your four fingers at v, curl it towards the direction of the magnetic field, and you will get a thumb in this direction, which is going to be the force. So basically this will be your force. Of course, I'm talking about a positive particle here. If in case we are talking about a negative particle here, if we are talking about a negative particle here, students, listen to me, students. Okay, if we are talking about a negative particle, it has a velocity v here, then of course we can again apply right hand thumb rule, v cross b. This is our direction for v cross b. Okay, this is our direction for v cross b, but force will be in the opposite direction, since charge is basically in the negative form. Since charge is basically in the negative form. If that is understood, the third thing I want to tell you here is that this force F, is going to be proportional to, is going to be proportional to, let's forget proportionality, is going to be equal to Q V cross B, And so there's three cases of this. Case one simply is what? Case one is your Q, the force on this Q on positive and negative charges are opposite. That means, just now I explained, if your Q is greater than 0, the force, if it is in this direction, if you get it this direction using right hand thumb rule, then in the negative charge, it will be opposite. Always remember, the force will always be opposite to in case of a negative charge. Second case we told, second case is basically V cross B. When I talk about V cross B, the force is going to be perpendicular. Force will always be perpendicular to the plane of V cross B, to velocity also and to magnetic field also. Force will always be perpendicular to the plane of the velocity and plane of the magnetic field. It can be described like this. If V is here and B is inside the plane, then the force is here. If V is here and magnetic field is basically inside the plane, the force is going to be 90 degrees with the velocity, and it's also going to be 90 degrees with the magnetic field, although I cannot show that here. If that is understood, let's go to the next case. This is all summary I'm trying to tell you. If you have any doubt here, please let me know. Also, we know that if V is equal to 0, since we know force is equal to Q V cross B, and if I say the velocity itself is 0, students, this is important. If velocity itself is 0, that means if I have a charge conductor here having a current I, and basically a charge here which is at rest where V is equal to 0, at that point I told you that due to charges flowing in opposite directions and having equal and opposite magnetic magnitudes, then because of that, there is not going to be any kind of a effect of magnetic force on this charge. Or you can see here that if you apply V is equal to 0, basically the force entirely becomes 0. This is an important concept. Third thing I told you is basically, if suppose we have a charge conductor here, forget a charge conductor. What I'm saying is basically, if we have velocity vector in this direction and the magnetic field also is in this direction, both are in the same direction, then what is theta equal to? Theta is going to be 0. Let's look at another case. Another case is where velocity vector is in this direction and your magnetic field is in this direction. In that case, theta will be 180 degrees. And so when you open the cross product, what are you going to get, students? Help me here. V sine theta. So what is going to be the answer? What is going to be your answer, students? Theta is 0, theta is 180. Force is going to be always 0. Force will be always equal to 0. Now, if that is understood, let's go to another concept here. I'm doing it quickly so that we are ready for the next lecture, maybe tomorrow or whatever. Let's see whether we have time. So right now, just now I told you that in a uniform magnetic field, students, in a uniform magnetic field, listen to me, uniform magnetic field, if I have a charged particle having some velocity here, then the force is always inside. The force at this point also will be inside. Due to this force, we are having this path. Due to this force, we are having this path. Due to this force, we are having this path. And so in this case, students, I know that my force is related somewhere to kinematics, where this force is basically centripetal force. We have studied this in gravitation, and so it is going to be mv square by r. And so also we know the relation in case of magnetism, moving charges and magnetism, that F is equal to Q V cross B. Please don't by heart this, just understand how we find out the relation. And so mv square upon r is going to be Q V cross B. Open up the cross product, you're going to get QVB. Sine theta is equal to 0. Theta is 0 because your velocity vector V and your magnetic field is perpendicular to each other. So theta is 90, sine 90 is 0. And so you have this formula, R is equal to mv upon qb. If you solve it, you will get mv upon qb. Just now we saw, if you understand this If you understand this concept, then it is easier to find out what time period is. Time period is basically the revolution of a charged particle in a circle or whatever, okay, at certain points. Now remember, students, listen to me. This is important. Although it's a summary, listen to me. Okay, we know that 2 pi by omega is what? 2 pi by omega, omega is angular frequency, omega is 2 pi, omega is v by r. You put that here, you get 2 pi r by v. What are you getting? 2 pi r by v. Now students, substituting the value of this radius here, substituting, you will see a major thing over here. You will see, please don't miss this. Please don't miss this. You will see that if I substitute 2 pi r by v and I substitute r value, I will get 2 pi by v. I can even find out the ratio r by v and directly put it, but mv by qb. In that case, v and v gets cut. What I'm getting? 2 pi m by qb. Students, listen to me here. That time period, look here, time period. What does it depend on? What does it depend on? Students, can you tell me? Time period, what is it depending on? Quick, tell me fast.
It is depending on the mass.
It is depending on the mass. Second thing, what is it depending on? Okay, it's depending on mass. Then
Charge.
it depends upon charge. Then
Charge.
it depends upon magnetic field. Then students, then okay, it depends upon all three. Can you see something important here? If I take this uniform magnetic field here and I give it a velocity which is very great, which is very large in magnitude, students, then will the time period change?
No, sir.
Will the time period change? So students, listen to me. This is important here. This is what I want to tell you. An important catch. Let it be whatever velocity. The time period does not depend upon it. Whatever velocity you send it. Okay. The magnetic field. Okay. The magnetic field will make sure that your time period is the same. Your magnetic field will make sure that your time period remains the same. Okay. The time period depends upon the mass and the charge and the magnetic field only. Okay, so this is important. It's a concept, students. We will see this in cyclotron. When we study cyclotron, we will see what is the meaning of this. Okay, so let's do, since we have 5 minutes, students, since we